Okay, I hope everyone had a good long weekend and you all got a chance to relax a little bit. So today and Friday, we're going to be talking in depth about permutation groups. So we've seen these as examples come up so far a little bit, but now we're going to really dive into the details on permutation groups, and we'll prove a couple of properties about them. And this is building up to something that we'll prove next Monday called Cayley's theorem, which says that, so this is like looking forward to Monday, Cayley's theorem, which says that every finite group is, and I'm going to put is in air quotes, a subgroup of a permutation group. So this theorem is really cool, and its proof is pretty interesting as well. And I think like the moral or the takeaway from this theorem is that like permutation groups are extremely complicated, and they actually like encapsulate all of finite group theory within them. This is sort of like our goal for the next couple of lectures. And building up to that, we're going to have to prove a bunch of properties about permutation groups, and we'll also introduce some like more efficient notation for writing down permutations. Okay, so just as a reminder, so a permutation of a set A is a bijective function from A to A. And bijective just means that it's injective and surjective. So in some way, you can just think of this function as reordering the elements of your set A. And then the symmetric group Sn is the set of all permutations on the set of 1 elements, which are just called 1 up to n. Okay, so in just a moment, I will introduce some notation for writing down permutations. Yeah, do you have a question?
I'm wondering why it's called a symmetric group.
I guess because it's like giving you all of the symmetries of just like n things. Yeah. Other questions? Okay, so first question is like, what is the order of Sn? So we can compute this as follows. So we have to write a bijective function from the set 1 up to n to the set 1 up to n. So for our choices of where to map 1, we have n total choices. And then for the second element, we can pick anything except for the element that we sent 1 to. So here we have n minus 1 choices, and so on. So then by the time we're deciding where to send n to, there's only 1 option left. So in total, this gives me n times n minus 1, and so on. Hold on. What do you need? and so on down to 1 as the number of bijections. So this is equal to n factorial. Okay, so the order, let me make a little room for this. So the order of Sn is n factorial. Okay, so now I'm going to introduce cycle notation. So how do we specify a permutation? Well, one way would be to just say what the permutation does to each element. So for example, consider this permutation that sends 1 to 2, 2 to 1, and this is going to be a permutation on 6 things. 3 goes to 4, 4 goes to 6, 5 goes to 5, and then 6 goes to 3. Okay, so this is a permutation on 6 things. And we could picture it as follows. So I could write down each of these 6 numbers. And just sort of draw what happens to each element. So 1 goes to 2, and 2 gets sent to 1. 3 goes to 4, 4 goes to 6, and 6 goes back to 3. And then the element 5 is fixed and is just sent to itself. So this is like one way that I could picture this permutation. And the idea of cycle notation is to basically take this picture and write it down in an efficient way. So what I'm going to do is just put each of these cycles into a set of parentheses. So from this, I would write 1 goes to 2, and then implicitly 2 goes back to 1. And then my next cycle would contain 3, 4, and 6 in that order. So 3, what does this mean? 3 goes to 4, 4 goes to 6, and 6 goes to 3. And then lastly, I would also have that 5 is contained in its own cycle. Okay, and then a couple of things about this. Typically, if something is contained in a cycle by itself, you would just drop that from the notation. And then also, as long as all of the numbers are single-digit numbers, which like in most of the examples that you'll consider, they will be single-digit numbers, you can omit the commas as well. So you would just write 1, 2, 3, 4, 6. And then in this, it's implicit that 5 is fixed. Does that make sense? Okay, so one other thing, I'm going to save that for later. Okay, so an expression of the form A1, comma, up to AM is called a cycle of length M, and it denotes the permutation where A sub I is sent to A sub I plus 1 mod M, or mod M plus 1, I guess, because that would send no, we want mod M. Yeah, okay, so this denotes this permutation. Okay, so let's just get a little bit of practice with multiplying cycles because of course this is a group and our operation is function composition, so I should be able to write down 2 cycles and know how to multiply them. So let's look at the following example. So let's let alpha, and this is on, I think I'm gonna have n equal to 8, and we'll let alpha be equal to 1, 3, 2, 7, 4, 5, 6, and then beta be equal to 1, 2, 3, 7, 6, 4, 8, and then 5 is fixed. Okay, so what is alpha beta, and what is beta alpha? So I'll do the first one, and then I'll give you a moment to think about what the second one should be. So alpha beta, what I'll do to start with is just write out all of the cycles at play. So first I'm just writing alpha, and then I'll write beta. And I could leave it like this, but typically you want to reduce expressions like this down to a product of disjoint cycles. So the way that we go about multiplying this is you work from right to left because function composition goes from right to left. And I usually just start with 1 and work my way up. So I'm first just going to wonder what happens to 1. So if I start over here, this cycle does not contain 1, so it does nothing to the element 1. If I look here, 1 is sent to 2. Okay, so now I need to keep track of what happens to 2. Here, 2 does not appear, and then in this one, 2 is sent to 7, and then from here, 7 is fixed. So overall, this product will send 1 to 7. Does that make sense? Okay, so now I'm just going to keep working through. So now I need to know, to figure out what comes next in this cycle that I'm writing down, I need to know what happens to 7. So working from right to left, here I have that 7 is sent to 1. And then after that, 1 is sent to 3. So 7 goes to 3. Then I need to know what happens to 3. Here, 3 is sent to 7, and then 7 is sent to 2. So that means that overall 3 goes to 2. And then finally, 2 goes to 3, and then 3 goes to 1. So that is the end of my first cycle. Does that make sense? Okay, so then when I'm deciding like what number to write next, I mean, it really doesn't matter. You could start with any number that hasn't been dealt with yet, but I just like to go in order. So 1 we've already done, 2 we've done, 3 we've done, and now we need to know what happens to 4. So 4 goes to 8, and then nothing happens to 8 after that. So 4 is sent to 8 overall. And then what happens to 8? 8 goes to 6, and 6 goes to 4. So that would be the end of that cycle. Okay, so we've done 1, 2, 3, 4. So now we need to do 5. 5 goes to 6. And then that's the end of it. And at this point, we've used up all the numbers, so we should be done, but we might as well just check. 6 goes to 4, and 4 goes to 5, and then 5 is fixed from thereafter, so 6 goes to 5. Okay, so this would be our final answer for how to write this product. as a product of disjoint cycles. Does this make sense? Do you all want to do the other product, beta alpha, and work it out? Okay, so I'll give you a few minutes to work out what beta alpha is, and then I'll just tell you the answer so you can check your work.
I'm sorry, I have a question.
Yeah.
Can you explain again why 6 goes to 4 and ultimately just goes to 5?
Yeah, so starting over here, so 6 goes to 4 in this permutation. And then moving leftwards, what then happens to 4 is 4 goes to 5. And then we need to know what happens to 5 over here, but 5 is fixed. So that means that like in total 6 is sent to 5.
But that feels like the stuff on the left is happening first. The stuff on the right happening.
The stuff on the right happens first, because like function composition, you do like, so what does this mean? It's like alpha represents some function and beta represents some function. So you're doing, you're applying beta first, and then you're applying alpha.
But if 6 is ultimately getting sent to 5, because 4 was sent to 5 first, that's where I'm getting confused. Like, I mean, sorry. Maybe I'll just
So, okay, so maybe let's like break this up. So like, what is beta of 5? Well, 5 is fixed. So, wait, was 5 what we were doing?
I think it was
6. So what is beta of 6? Beta of 6 would be 4. So then we want to do what is alpha of beta of 6. So that's going to be alpha of 4. And alpha of 4 is 5. Yeah. Other questions? Yeah.
Is there any significance to the fact that 1732 was in both orders?
I don't know. Yeah, I'm not sure. Is this, did everyone get agreement with this product? Okay, good. So, then let's prove a couple of first properties about permutations. So I guess like the first thing is that we need to prove that like this cycle notation actually works. So what I mean by that is the following. So we'll have a theorem. It says that every permutation of a finite set can be written as a cycle or as a product of disjoint cycles. Okay, so this is sort of actually telling us that, that this will work. And the significance of the cycles being disjoint will become clear after the next theorem. But the next theorem says that when the cycles are disjoint, they commute. So it doesn't matter what order you write the disjoint cycles in. And so that's why it is important to be able to write your permutations as products of disjoint cycles. Okay, so let's prove this. So I'm going to let alpha be a permutation on the finite set A, which will be the numbers 1 up to n. And then what we're going to do is write alpha as a product of disjoint cycles. As follows. So the first thing that I'm going to do is just let A1 be any element of A. And then I'm going to set A2 to be alpha of 1, or sorry, alpha of A1. I'm going to set A3 to be alpha squared of A1, and so on. So we know that this sequence of powers of alpha applied to A1, this has to be finite because the set A is finite. So for some M, we have, or let's do this. So we know that if I keep writing down subsequent powers of alpha of A1, we're going to have some I and j with alpha to the I of A1 equal to alpha to the j of A1, just because this sequence has to have repetitions in it. And then we can solve this for A1. So let's just suppose that I is greater than j. So then we would have alpha to the I minus j of A1 equal to A1. Okay, so then we have like our first cycle. So we have that A1 goes to A2, A2 goes to A3, and so on up to A to the I minus j. And then ai minus j. Sorry, I just want to check that I got the indexing on this right. So a sub I minus j plus 1 would be the one where I have alpha to the power I minus j. So so this would be a cycle. And this describes what the permutation alpha does to those elements. So as our second step in writing alpha as a product of disjoint cycles, there may still be like unused elements of A. So then in this case, we would select a B1 from the set A, take away all of the A1s. And then create a new cycle. Which would look something like B1, B2, and so on up to B, let's just call it B sub k. And this has no elements in common with the previous cycle. And we see this as follows. So for contradiction, let's suppose that alpha to the I of A1 is equal to alpha to the j of B1 for some I and j. But then that would mean, so this is a new I, and maybe I should just use different variables. Let's just call this S and T. So for some S and T. But then alpha to the S minus T of A1 is equal to B1. So that means that B1 would have already appeared in our A list, which contradicts the way that B1 was selected. So this contradicts how B1 was selected. So that means that the A cycle and the B cycle are in fact disjoint. And so we can continue in this way, creating new cycles until all elements of A have been used. And that completes the proof. Are there questions? Yeah.
For the indexing for like I minus j, would it be I minus j minus 1 or plus 1?
Yeah, did I get this wrong? So what I want this element to be is alpha to the I minus j of A1. And the index is in, like, for example, these cases, the index tells you is 1 higher than the power of alpha. So I think that's okay. Do people agree or disagree? Yeah.
Wouldn't A alpha to the I minus j
Yes, okay, yeah, perfect. Okay, so this is equal to A1. So I actually want to only go up to the one that gives you alpha to the I minus j minus 1. So yeah, so this one should be like that. Okay. Good. Yeah.
One question about alpha to the s from A1 equals like alpha to the t to B1, and then how you go from that step to the step to the next step.
Yeah, so alpha is an element of a group. So it has, and so is alpha to the t. So it has an inverse. And so I can multiply both sides by alpha to the minus t. And so that gives us this, equation. Other questions? Okay, so now we will prove that disjoint cycles commute, so it actually doesn't matter what order you write these disjoint cycles in. So this says that if the pair of cycles alpha, which is, let's just say it's A1 up to AM, and beta, which we'll say is B1 up to BN. So if they have no entries in common, so if they're disjoint, then alpha beta is equal to beta alpha. Okay, so the proof of this is going to be quite straightforward. So basically, we are just going to apply each of these permutations to an element X and observe that it does the same thing in both cases. But it will depend on what type of element that is, right? Because if that is one of the B sub i's, then beta will do something to it. If it's one of the A sub i's, then alpha will do something to it. And if it lies outside of either of those cycles, then that is yet another case. So let's say the set that we're working with, A, is consists of the A's, the B's, and then some other elements, C, that are not involved in these cycles. By the way, just like a piece of terminology that I feel like comes up sometimes, this set A is sometimes referred to as the ground set. So sometimes it comes up that you're dealing with permutations on a set that's not necessarily just the elements 1 up to n, and so you call that the ground set. Yeah.
And same in the theorem, do you mean to write beta equals B1 or beta multiplies?
Oh yeah. Oop. I need to separate this. Yeah, good catch. Any other questions? Yeah.
So by saying that A is the ground set, do you mean that like if you do some permutation to set A, then it becomes a different set, like the order matters?
No, the order doesn't really matter. Yeah.
Okay.
Yeah. Other questions? Okay, so this is our set A, and then we're going to prove that for all x in S, alpha beta of x is equal to beta alpha of x. And so there's going to be just 3 separate cases depending upon if x is an a sub I, a b sub I, or a c sub I. So if x is equal to an a sub I, let's look at that case first. So that would mean that alpha beta of a sub I, well, what is this? Beta fixes all of the a sub i's, so this would be alpha of a sub I, and alpha of a sub I, so alpha is a cycle that's just going to send a sub I to a sub I plus 1. So this becomes a sub I plus 1. Then for the other computation, beta alpha of a sub I, so again, alpha gives us alpha of a sub I will be a sub I plus 1. So this becomes beta of a sub I plus 1. And then beta fixes the a sub i's, so this gives me a sub I plus 1. Okay, so we have agreement in these 2 cases, so that one is good. And then the second case is when x is a b sub I. And this is going to work out just by a similar argument to 1. And then for the third case, if x is a c sub I, then what's going to happen is alpha and beta both do nothing to c sub I. So alpha beta ci becomes alpha ci, but then that just is ci. And on the flip side, we have beta alpha of ci is equal to, well, alpha does nothing to ci, so this is beta of ci. But then beta does nothing to ci, so this is ci again. And then that would finish the proof. Are there questions about this? About how this proof went? Okay, so let's continue on with the facts about permutations. So, So I think the next kind of like natural thing to wonder is how to compute the order of a permutation that is written in cycle notation. And it turns out that it is super easy to read off the order of an element when it's written in disjoint cycle notation. So this theorem says that the order of a permutation on a finite set written in disjoint cycle form is the least common multiple of the lengths of the cycles. Is the statement clear? Yeah.
Order implies that there's like an identity partition, so just like the one where each element is mapped to itself.
Mm-hmm. Yeah, okay, yeah. So the identity element is the one that fixes every element of the ground set. So you could write it like this, just with each thing in its own cycle. But usually you omit these, and so typically people will just write E for the identity element because it's like, it's an empty set of cycles. Yeah. Other questions? Okay, so let's prove this. Hopefully we have time, but if we don't, we can finish the proof next time. So first let's compute the order of a cycle of length n. So that'll be our first step. So a cycle of length n has order n. Actually, I'm going to give you a few minutes to think about this part of the proof, and then we can discuss it. Okay, so why does a cycle of length n have order n? Yeah,
So say we have a cycle, A1 to AN.
yeah,
Any arbitrary AI, it takes, let's say the cycle is alpha, it takes alpha to the end of AI to become AI again, and that's because I plus n mod n is
yeah. Yeah, so alpha to the n of AI, this is just gonna like add n to the index of AI, but then we're doing this mod n, so this is gonna give me a sub I. So that tells me, so the order is the least number n such that alpha to that n is the identity. So we found a and n such that alpha to that n is the identity. So what did this show? This shows alpha to the n is equal to the identity. So why is there no smaller n that does this? Yeah.
And this isn't like a complete proof, but I think the general idea would be that you assume that there is such an n, and then that would imply that there is a cycle of length less than n here. But we assume the cycles are disjoint, and that would mean that there are like two cycles that share some elements. So it can't be that there's a small.
Yeah, so let's suppose alpha to the k is equal to the identity. Then if I apply alpha to the k to a sub I, then we know that that's equal to a sub I plus k, and that's also supposed to be a sub I. So that means that n divides k. So k has to be at least n. Yeah. Okay, so I'm going to stop there for today. So we've done the proof in the case that your permutation consists of one single cycle, and next time we'll just start with proving, we'll do the general case of the theorem, and then also next time we're going to prove some more properties about permutations, like leading up to Cayley's theorem. Hey man, what is this about? Why you bark? What? Hey, dude. Dude. Do you have a question?
What kind of just like similar to the problem
I would say like definitely expect some things that look like problem set problems, so I might also do like some because I like
Thank you.
yeah. You have a question?
Yeah, so I'm just not sure, like, why do we know this is true? Intuitively, we know it's true, but why do we know that a sub I plus n equals to?
Because like, so what this, like what permutation is this cycle giving you? It's the one that sends like a sub I goes to a sub I plus 1, but you have to think of it mod n. A sub n goes to a1.
Okay, so
Yeah.
then when you do mod n over here, the m goes away.
Yeah, yeah, yeah. So the index is always mod n.
Okay.
I left my water bottle. How was your long weekend?
Not long enough, but but it was fine but busy.
Yeah,
Yeah. How about yours?
it was good. Yeah, got a chance to relax a little bit. I don't teach on Tuesdays, so mine was like extra long.
Mm.
Yeah.
Oh my
Did I
goodness.
leave anything else up there? Or is this
I think it's all good. Hello. It's okay. Yeah. How about you? I want to ask you, at some point, do you use Canvas to collect papers, to collect essays? I might want to talk to you about how that works, because I'm completely ignorant. Yeah, at some point. Is that?